there are actually several aspects to this, and each of the aspects has its own issue. It's not isolated to just what Charles Steinhardt and his group did, although they did a very thorough analysis of all of the available data and put together a pretty convincing case, I would say. But this problem with the too early appearance of galaxies actually goes back a couple of years, and there were already hints that there were major issues with the standard model. And basically, to put it in a nutshell, what it is that in the standard model of cosmology, there's a very firm prediction of what the timeline has been since the Big Bang in terms of how much time has elapsed for a given redshift. You know, when we make measurements, we don't really measure quantities based on time. We measure them based on redshift because that's what we can see. We can see how much the wavelength of the light has shifted, and there's no question that we understand what the redshift is. But in the standard model of cosmology, there's a one-to-one relationship between the redshift and the age of the universe at various points in our past. And the problem here is that these massive galaxies and the massive dark matter halos from which they formed appeared way too early for standard astrophysics to be able to explain how they came to be. So just to put a number on this, because it's a lot easier, I think, to understand in terms of actual numbers, the redshift at which they see these massive galaxies and halos, which is around 10 in the case of Charles Steinhardt's work, that corresponds to an age of the universe of around, let's say, 600 million years after the Big Bang. And remember that the age today is about 13.7 billion years. So we're talking about something very, very early in the history of the universe, 600 million years or so. The reason that's a major problem is because, as we understand it today, stars could not have started to form until about 3, maybe 400 million years after the Big Bang, because it would have taken that much time for the gas to cool and condense and clump up and form stars. So basically what the data are telling us is that if the standard model of cosmology is correct with its timeline, then these 10 to the 9, 10 to the 10 solar mass galaxies, billions of solar masses within each galaxy, formed in only 150 to 200 million years, which is absolutely physically impossible as far as we know today, based on the astrophysics of star formation and aggregation and the formation of galaxies and so forth. So that's why they labeled this the impossibly early galaxy problem. But to be fair, you know, there were other indicators even before Steinhardt's work that showed that there was a problem with the timeline. Perhaps most famously with the appearance of these supermassive quasars, these supermassive black holes, which started appearing at a redshift of 6, and then today the record is about 7.4. That redshift corresponds to about 800 million years. And so the indication from the appearance of these supermassive black holes so early in the history of the universe is that these billion solar mass objects formed in only, 500 million years, which again is not easy to understand in terms of the astrophysics that we know today, because they either would have had to have been born already having a mass of hundreds of thousands of solar masses, which we don't see anywhere in the universe. There's no indication that something like that could have happened, or that they were accreting matter from their environment at prodigious rates, well beyond what, again, astrophysics tells us is possible. So you see, the conundrum is that we see these objects, either black holes or these massive galaxies, way too early, and in order for us to be able to explain how they formed in such a short time, we have to exceed what we think can actually happen in terms of the astrophysics of accretion and growth and so forth. So the conclusion from this is either that the astrophysics we have today is wrong, or what we're suggesting is that perhaps the cosmology is not completely right. And, it turns out that there are other indicators that suggest that the timeline in the early evolution of the universe was actually perhaps twice as long as what the standard model predicts. And so instead of, these objects appearing at 900 million years, they would have appeared at 1.7, 1.8 billion years. And it turns out that by just doubling that timeline, it removes all of the problems, either with the quasars or the galaxies or with these massive dark matter halos that Charles Steinhardt is talking about. So that's what the issue is, and that's what the point of our paper was, is to, again, affirm this developing idea that perhaps the timeline is wrong. It's not that the astrophysics is wrong, but we just don't have the right final version of the cosmology yet. It still needs to be tweaked. When you apply a cosmological model, what that model does is it tells us how rapidly the universe expanded instant by instant in its past. And based on that expansion rate, then one can form a one-to-one mapping between the redshift and the age of the universe. So the redshift is untouchable. That's what it is. We measure it, and that's what it is. But when you try to infer the age of the universe at a given redshift, that depends critically on the cosmological model that you adopt. And as I say, the main difference between different models is the rate of expansion instant by instant in its past. So basically, what it's starting to look like is that the expansion rate in the standard model is not quite right. It was a little bit too decelerated at the beginning. And we're not talking about a huge difference. So the model is, the standard model of cosmology is not wrong. That wouldn't be the right way to say it, but it's not in its final version. It needs some tweaks and some adjustments, to make it be more consistent with all of the available data. And what we're talking about is a factor of 2 difference. So, beyond a redshift of 6, at a redshift of 6, the standard model suggests that the age of the universe is about 930 million years after the Big Bang, but what it's starting to look like is that it should be closer to 1.7 billion years, roughly a factor of 2 longer. So yeah, it's not insignificant, but it's not a huge overhaul. So it wouldn't be right to say that the standard model is wrong, completely wrong. It's just that it's an approximation which needs to be perfected somehow, and with this change, which is not so severe, to be honest with you, changing the timeline by a factor of 2 is not that severe, then it makes all of these other paradoxes go away, and everything fits within the astrophysics that we understand today. So it's either the astrophysics is wrong, or the cosmology needs to be adjusted. That's the point, right? And it's hard to see how the astrophysics is wrong, because it seems to work everywhere else where we apply it, especially in the local universe. So, we're in the camp where we think it's more likely that the cosmology needs to evolve and be perfected rather than the astrophysics needs to be thrown out and replaced with something else. Yes, it would. Actually, it has far-reaching consequences, even well beyond that. But directly answering that question, yes, because it would mean that the temperature would be lower at the redshift where this line was measured, which would be consistent with what they're finding. But one has to be careful, because that measurement seems to be susceptible to systematic problems, systematic errors, and there have been some counterclaims made that perhaps the measurement is overstated, that one has to be careful dealing with the systematic errors that would lead to something like that. So it's probably premature to jump on that bandwagon, but if it's a correct measurement, then it would suggest that the temperature was lower at that redshift, which would be consistent with this doubling of the timeline and reducing the expansion rate. Yes, so it would be consistent with that. But there are other consequences that are even more significant. Everybody's heard of inflation. And the standard model of cosmology can't survive without a period of inflation in its early history. It turns out that the horizon problem, which gave rise to the inflationary paradigm, the horizon problem can be related or understood in the context of this timeline. The problem is that the universe decelerated too fast, so the timeline was too short for different parts of the sky to come into equilibrium, which is what we see today. And it turns out that this doubling of the timeline actually completely eliminates the horizon problem, completely. And so it does away with the need for inflation. And the reason that's interesting, and by the way, ironically, Charles Steinhardt's father, Paul Steinhardt, was one of the inventors of inflation. And Paul Steinhardt is now a total convert the other way. He thinks that inflation is wrong. Even though he was one of the inventors of that, he's actually an inflationary apostate, if I could put it that way. He argues against it. So he thinks that the evidence is pointing against inflation also. But the nice thing about this timeline issue is that it does have other significant consequences, like possibly removing the need for inflation. And, the reality is that today we're, 38 years after inflation was invented. And even after almost 4 decades, we still don't understand how it worked. Inflation is not so much a model as it is a concept, and there are different ways of making inflation happen, but it's impossible to pin it down exactly and make it very strongly predictive. So that's why even after 4 decades, we still don't have solid confirmation that inflation happened and what the properties of the inflaton field were. It's just very nebulous, very ambiguous how all of it could have worked, which perhaps is an indication that it never really happened, because if it did, there would have been some solid physical explanation for how it should work and what its predictions are. And it's intriguing that now that the observations are getting better and better, and we're getting more precise measurements at high redshift, meaning early in the universe's history, we're starting to see evidence that the timeline just isn't right. And, if the timeline, as I say, is double what the current standard model predicts, then it removes the need for inflation. Isn't that amazing? That after almost 4 decades, trying to make inflation work and not being completely successful, perhaps now we're at the point where we can start to do away with it. And, the reason that it hasn't worked so well is because maybe it just never happened. Now that you went into the CMB, there are other aspects there that are partially related to the timeline problem with galaxies, but also there are other issues. So the picture that we have of the CMB today is that it was the CMB was produced as a result of decoupling. When radiation decoupled from matter because the various charges combine to form neutral hydrogen and so forth. And the picture is that all of this happened about 380,000 years after the Big Bang, very, very early on, right? Much earlier than star formation and eventual galaxy formation and so forth. But the honest truth is that this is all theory. We don't actually have any hardcore evidence that that's really where the CMB happened, where it was produced, and that was the mechanism that produced it. We don't see recombination lines, for example. And it's true that the sensitivity of the instruments is not yet great enough for us to have conclusively detected the lines, but until we actually see recombination lines, this idea that the CMB was produced by recombination is just a theory. There's no experimental verification that it happened. And perhaps even more tellingly, if the picture of the CMB having been produced early on as a result of recombination is correct, then there shouldn't be any frequency dependence in the fluctuation spectrum. In other words, the spectrum was produced in a medium where the most important physical process, Thomson scattering, is independent of wavelength of the light. But yet, when we look at the data from Planck, say, we do see evidence that the spectrum of fluctuation changes with wavelength. So that again argues against the recombination picture. We don't have a compelling argument yet, but what I'm getting at is that this notion that the CMB was produced 380,000 years after the Big Bang due to recombination does not have yet any experimental confirmation. On the other hand, it's possible that the CMB may have been formed in part due to dust processes. And if you look back and ask when would the dust have been injected into the intergalactic medium, it would have been at the time when population 3 stars started forming, which actually corresponds to a redshift of about 15, not the redshift of 1081, which is what we currently think is where the CMB was formed. So all of these upcoming missions and measurements will tie into this general question of when did the CMB actually form? Or was it really associated somehow, directly or indirectly, with the process of star formation itself as a result of the dust that these stars injected into the interstellar and intergalactic medium, which then would mean that the CMB was perhaps formed at only a redshift of 15 rather than a redshift of over 1,000. So you can see how there are different aspects that one has to cover with the CMB, but ultimately there is a significant overlap with the process of large-scale structure formation and the timing that's associated with that. That's quite a big difference. You know, the CMB either emerged 380,000 years after the Big Bang, or it would have emerged over 1 billion years later, when stars started forming. And insofar as the current observations are concerned, we wouldn't be able to tell the difference just yet. So what we're hoping to see is telltale signs of either recombination or dust processes in forming it, which means, you know, we're hoping to see recombination lines, or we're hoping to see a very weak or no dependence of the spectrum on frequency. So all of this is something to look forward to over the next 3, 4, 5 years. Things will change dramatically, it seems.